Hi guys, hope you're well. This is one of my favourite topics in statistics. I really love it. I have to apologise for the last video, by the way. When I heard it back, there's a little bit of rustling, and it's because I kept moving my iPad around. So I'll try not to do that today. I do apologise. There was quite a lot of noise in the background, so I'll try and be better today. You'll notice there's a lot of new terminology here that you've not seen before. We've got discrete random variables, continuous random variables. Well, we know discrete and continuous data. Probability distributions, probability density functions, and continuous distribution functions. Loads of different things we'll touch on over the next couple of lessons. Don't worry too much about the terminology. You will get it over time. Let's go straight into an example, and it will become a lot more obvious as we go into it what the terminology all means. So we've got an example here with Richard. He's having a go at a game where he's got to throw balls into a bucket. The probability that he succeeds is 0.3. So I'm going to class the ball going into the bucket as a success, and the fail is if it doesn't go in. And the success and fail are terms that I will use loads when we get onto binomial distribution, so it makes sense to introduce them now. If he gets 2 or more in, he wins a prize. Brilliant. Okay, so what we've got here is a random variable. So x is a random variable. It's actually a discrete random variable because the data can only take discrete values. So x can take a variety of values here. So x is going to be the number of balls he gets in the bucket. Well, there's a couple of examples here, possibilities here. X could be 0, he doesn't get any in. He could get 1, he could get 2, he could get all 3 in. So what we're going to do is put this into a table, and this table will be called the probability distribution. I'm probably making this a little bit too small. So x can be 0, it can be 1, it can be 2, let me add on the end here, it can be 3. And what we have is the probability that the random variable x takes each of these little individual values. So we're going to work out the probability that x could be 0, x could be 1, x could be 2, x could be 3. And then this overall is called the probability distribution. It shows us the probabilities related to each of these values occurring. So let's have a look at what's happening here. So Richard is throwing balls into a bucket. He could get no balls into that bucket. Well, the probability that he fails is 0.7. So he's got to fail on all 3 attempts. So fail and fail and fail and fail is 0.43. Next ones are slightly harder. So think about how he could get 1 ball in that bucket. He could get it on the first attempt and then fail twice more. He could fail, succeed, fail, or he could fail, fail, succeed. So you've got 3 different possibilities there. He could get success, fail, fail. It could be fail, success, fail, or fail, fail, success. So we've actually got this same calculation but 3 times over. So what I'm going to do is delete that and instead just put a 3 in front of it, and hopefully you'll see why in a second. So I've got 3 different ways of getting that possible outcome there, so 0.441. So that's going to go in here. Okay, probability of getting 2 balls in. Again, so there's different possibilities here. He could succeed, fail. He could fail, succeed, or he could succeed, fail, succeed. Again, it's the same 3 numbers times each other, but there's 3 options. So I'm going to put a 3 in front of that, and that comes out to be 0.189. And I'm sure those amongst you who are, you know, on the ball and not half asleep would be like, well, surely just to fill in that one, we can just take it all away from 1. And yes, you can. But let's do it the long way anyway. So probability that he gets all 3 in, well, there's only one way that can happen, isn't there? He succeeds, he succeeds, he succeeds. That's 0.027. But yes, we certainly could have just taken the other numbers away from 1. But I wanted you to try and notice something. It's not too important to take it in now, but it will be when we look at binomials. So I'm going to try and show you that in front of this, we've only got one outcome, haven't we? There's only one way of getting that. There's the 3 here, the 3 here, and there's a 1 here. I don't know whether you recognise those numbers at all, but it's actually the 3rd line of Pascal's triangle, and that's quite important. So he's doing 3 attempts at something, and there's 1 way of getting this, 3 ways of getting this, 3 ways of getting this, 1 way of getting that. You'll actually find that the binomial coefficients, Pascal's coefficients, come up an awful lot in these kind of problems, and they can make your life a lot easier. So rather than working out all 3 possibilities, I could have just known it would be 3C1, 3C2. Don't worry too much about that for now. We'll look at that in more detail. I just thought it was quite interesting to see the 1, 3, 3 and the 1. So over here we have got our probability distribution. So this is our probability distribution for what's happening up here. We know what the probabilities are. If we plot them, you get a graph like this. Okay, this is actually a positive skew. And sometimes you will be asked to actually plot the diagram. And it's always worth doing a diagram like this, because you can kind of imagine what it would look like if you had a curve drawn over the top of it. And that graph is called a probability density function. Okay. If you're dealing with discrete data, you want to draw a line graph. If it's continuous, you are a lot better using a curve. So bear that in mind. Right, so I've already talked about probability distributions, and you've probably already noticed this as well. So that basically says that the sum of all the probabilities has to be 1. And if you've got a table with 3 values already filled in, to find the 4th one, just take it away from 1 to make your life easier. So back here, I would probably have been better off working out 0 and 3 because they were easier. Maybe working out this one and then doing that one by taking them all away from 1. Okay, I've got another situation here, and X is the random variable, the number that appears on the dice. X can be 1, 2, 3, 4, 5 or 6, okay? Now, because they're all going to be the same probability, I can write this in one of two ways. I can just do a table, because I'm sure we all agree that the probabilities here are all going to be a sixth. I could write it as a kind of function. They're sometimes called like piecewise functions. So the probability is a 6 for x equals 1, 2, 3, 4, 5, 6. And then you'd have a little situation here where you're saying naught otherwise. Don't worry if you don't like that. We'll do a little bit more on that in the future. It just seems a bit tedious to do a table like this when you could easily use a function. So these would all be a sixth, because the probability of getting each of these numbers on the dice is the same. This has got a special name. This is called a uniform distribution, because all the probabilities are the same, so that it's uniform. And if I wanted to sketch that, I'm going to try and do a really poor sketch down here. I won't do a scale because I think you'll understand what I'm trying to achieve. But all these lines will be the same height. So they would all be at a sixth. And this would be 1, 2, 3, 4, 5, 6. So a uniform distribution, you'll sometimes see it referred to as rectangular. Because if you just blocked it in, it certainly would look like a rectangle, wouldn't it? And the area below it, if we had a line across there, would be a rectangle. Okay, I'm going to look at one more with you. And this is a very common exam style question. Very, very common. So we've got a discrete random variable. We have no knowledge of what it is. We don't know whether it's Richard doing a game on the fair. We don't know whether it's a dice or whatever. But it's a situation where x can be 0, 1, 2, 3 or 4. And these are the probabilities associated with it. Only this time we've got a letter in here, so we haven't got all the probabilities. Question A, find the value of C. Well, we need to use our knowledge here that all of these here are going to add up to 1. So, for part A, 3C plus C plus 0.3 plus 0.2 plus 0.1 must equal 1. So 4C plus 0.6 equals 1. C must be 0.1. So now we know that's 0.1. We actually know that is 0.3 and that is 0.1. So whatever situation this is, these are the probabilities associated with each of these. So it's more likely to get a 0 or a 2. It's less likely to get 1 or 4, whatever this is. Now in part B, it's asked us to work out the probability that x is less than or equal to 2. Well, this is actually a lot easier than it initially looks, because if x can be 2 or less, any of these would be fine. So let's imagine it's some weird dice that I'm rolling. I want any value 2 or less. So it could be 0, it could be 1, it could be 2. So I would be happy with the probability of 0, 1 and 2. So that is going to be 0.3, 0.1, 0.3, and that all adds up to 0.7. I hope that hasn't been as difficult as it sometimes comes across to be. It's very new. I know there's a lot of new terminology, a lot of new notation. It is quite challenging to begin with. But when you realise it's just probabilities and looking at specific situations where probabilities add to 1, and sometimes you've got a uniform distribution where all the probabilities are the same, it's not too bad. I think it's the terms PDFs and DRVs which make it all a little bit more confusing. So have a go at the questions on the chapter checklist. Again, any you don't understand, let me know, because after this we'll be looking at continuous ones. So unless you follow it for discrete, you will struggle with the continuous ones. So have a go. Let me know how you get on. Any help, please contact me and I'll be more than happy to reply. Right, take care. Hope you're well. Look after yourselves. Bye for now.